This meeting is being recorded.
For problem 1 from chapter 15, we are asked to determine for each of these compounds whether or not the two protons shown in red are homotopic, enantiotopic, or diastereotopic. So if you recall, if we can find an axis of symmetry, then we know that we would have or we could have homotopic protons if we were to exchange them, and they would be equivalent compounds. So remember, if you say apply an axis of symmetry here and rotate, close your eyes, will this proton be the same as this proton? Well, yes. So we can do our replacement test as well. We could replace one at a time with a deuterium, and then we could determine whether or not they are equivalent protons using the replacement method. But in this case, if you recall, benzene here rings, those double bonds really do not apply to our symmetry as they are all equivalent. So what we would see here would be a compound that looks like this. So either of these two protons shown here would therefore be homotopic. So we can see that these are equivalent, and with the replacement test, we would have the same compound. So let's take a look at compound B, right? So we'll define these first before we move on. In compound B now, so we see one proton here on a wedge, the other on a dash. So this compound we would find, we could not find an axis of symmetry, but a plane of symmetry could be proposed. The same plane with the molecule is within, actually. So in conclusion, we could also do the replacement test, therefore, and conclude that we have enantiotopic protons shown here, right? Because if we replaced one at a time and then did the mirror image of one compound to another, we would see that these are enantiomers. So these would be enantiotopic, these two hydrogens. Let's move to our third compound here. So in this case, we cannot interchange these protons through rotational symmetry. We cannot find an axis of rotation. Also, there's no plane of symmetry that divides this molecule equally, this compound equally. We can see that we have this hydrogen on a dash, or on a wedge rather, as is this hydroxyl group. So if we did our replacement test, so say we replaced one or the other of these with a D here, we would see that these hydrogens are diastereotopic because the compounds are diastereomers. Diastereotopic. Okay. Now, let's take a look at our compound D here, and through using these same analyses methods, we would determine whether or not we have an axis of rotation, or if we have a plane of symmetry. So we do not have any rotational symmetry, so we could rule out that these are homotopic, but there is a reflectional plane of symmetry. So if we divided this molecule in the same plane that it is, we could see that these two protons are enantiotopic. And then through the replacement test, we could replace one or the other, and we would find enantiomers. So for those reasons, we have enantiotopic protons shown here in compound D. And compound E, we can find an axis of symmetry that we could rotate this molecule around, and we close our eyes. When we open them, we don't know that the protons are switched, so through that method or the replacement test, we could replace one with a deuterated proton here, and either method we would confirm that these are homotopic, these are completely equivalent hydrogens, and for the reason of the axis of reflection, the axis of symmetry, or the plane of reflection, the mirror image with the replacement test. We know that E has homotopic protons.